Welcome back to part 2 of, what are we looking at here, of the section 5.3 Fundamental Theorem of Calculus. All right, so here's our last example, and then we'll move on to the second part of this section. Our job is to find the area of the region bounded by the graph of this parabola, y equals blah, 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 blah. The x-axis and the vertical line 0 and 2. Okay, I need to know what this looks like. So I'm going to come over here to my graphing calculator. I'm going to graph this thing. So y equals 2x raised to the second plus 3x, was that right? Minus 3x plus 2. Minus 3x plus 2. I'm going to graph the vertical lines x equals 2. And what was the other vertical line? X equals 0. And so it looks like, if I flip this over projector mode, they want us to find that area right in there. The area between this. So this looks like an integration problem. Oh, I can do this. So if I make a quick sketch over here, we were looking at this, right? So they want this piece right there. And if that's the bounded region, then we're looking at doing a definite integral from 0 to 2 of 2x squared minus 3x plus 2 dx. It's a definite integral because we're finding the area bounded by the curve in the x-axis. Lower limit of 0 for one of my vertical lines, upper limit of 2 for the other vertical line, bounded by the x-axis and the curve. So it's this piece of area right in here. And so I'm going to find this by doing a definite integral. So this is my little f. I need to find the big F, the antiderivative, or an antiderivative of that. 3 terms, term by term. Antiderivative of the first term is going to be 2/3 x cubed. Antiderivative of the second term is going to be a negative 3/2 x squared. Antiderivative of the third term is going to be 2x. And this whole thing needs to be evaluated from 0 to 2. Now, I happen to love when one of my limits of integration is 0. Because think about it. When I plug that in, when I do the f of b minus f of a business, it's going to be minus f of 0. And what's going to be our f of 0 for this? I'll give you a second. That's right, our f of 0 is going to be 0. So all I really need to do is plug in the 2, and that will give me my answer for my problem. So I'm going to have 2/3 times 2 cubed minus 3/2 times 2 squared plus 2 times 2. Now, just as a note, because some people like to take things way too literally, am I trying to say here that every time I see a 0 as a limit, I could ignore it? No, that is not what I'm saying here. I'm saying that for this problem, because it is a polynomial, I can ignore it because the evaluation there at 0 will be 0. But if there was trig involved or something else, then I'd have to rethink it because some functions, when you plug in 0, you don't get 0. All right, so back to the problem at hand. Let's see, 2 cubed is 8. So working on the first term here. 2 cubed is 8. That's going to give me 16/3 minus 2 squared is 4, so minus 12/2 plus 4. 12/2 is 6. So I have 16/3 minus 2. Let's see, 16/3 minus 2 is 10/3. So the value of my integral, or the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis and the vertical lines x equals 0 and x equals 2 is 10/3 units. So 10/3 units squared, whatever those units would be. Okay. All right, so now we're actually going to take a look at the true full fundamental theorem of calculus. We were actually only so far using part 2 of the fundamental theorem of calculus. Part 1 of the fundamental theorem of calculus is actually a little bit trickier to read. So let's take a look at what part 1 says. So for the fundamental theorem of calculus, we're going to suppose that we have some function whose name is little f, and little f is a continuous function on the interval a to b, and it is a closed interval a to b. Then part 1 reads, if g of x is equal to the integral from a to x of f of t dt, then g prime is just equal to f. Now you might be asking yourself, what? So let's take a look at what this means. Okay? I'm going to come back up here because I have some space. It's an if-then statement, right? It says if g of x is equal to the integral from a to x of f of t dt, then g prime of x is just equal to f of x. Okay. I'm going to work this left-hand side out. Okay. According to part 2 of the fundamental theorem of calculus, this integral right here is going to be equal to big F of x minus big F of a. And how did I get there so quickly? Well, if my integrand is little f, then my antiderivative is big F. And it's at the upper limit minus the lower limit. Right? So there's my function. Right? Good so far? Okay. So then if I took the derivative of this whole thing, well, derivative of g of x then is g prime of x. Derivative of big F of x, I need to take the derivative with respect to x of big F of x minus the derivative with respect to x of f of a. Okay? I'm going to deal with the second one first. If a is a constant, then f of a, the whole thing, is just a number. And what's the derivative of a number that contains no variables? That's going to be equal to 0. Now over here we're saying, what is the derivative of big F? Well, what's the relationship between little f and big F? Well, big F is the antiderivative of little f, or little f is the derivative of big F. So if I'm taking the derivative of big F, I'm just getting little f. And so then what's little f minus 0? Just little f, which is the then part of the statement. All right, somebody wants a geometry argument for this. So let's take a look at the original problem in terms of geometry. Okay. Here's the if part. It says that if you have a function and what it does is it adds up the area under that curve, what are you going to get when you take its derivative? Well, the rate of change of the function g. So if this area is found by just taking that number and plugging in the g, then how it's changing is that little piece that gets added on. Well, that little piece that gets added on has a height of f of x and a width of delta x. So the area of the new piece is f of x times delta x, and if delta x is really, really small, then the area of this thing essentially becomes just its height, and its height is just f of x. All right. Now I know there's at least one person who's confused, and they're like, what do I need to know? Well, here's what you need to know. If someone hands you this relationship and wants you to find that, all you do is you take that second function, plug in x, and call it done. right? So, here you go. What's the derivative of the integral from 0 to x of 3? That was weird. 3t dt? 3x. Because what's this? Oh, that's f of t. And when I take the derivative of an integral, I take the integrand and I plug in the upper limit of integration, provided that that variable matches that variable. If those aren't the same, and if that isn't a constant, then the math starts to fall apart. We have to treat it differently. Okay. So if f is equal to this, what's f prime? Well, what do you do when you take the derivative of the integral? You call this little f of x, or in this case f of t, and you plug in the upper limit. Oh. Taking the derivative of an integral, constant value x, function, secant squared x, and I'm done. Taking the derivative of an integral, constant, variable, function, square root of x squared plus 1, and I'm done. Okay, new one. Harder. What changed? Well, the upper limit is no longer just plain old x. And since the upper limit is no longer plain old x, we get to use the chain rule. And so what ends up happening here is f prime. Remember, if you're calling the whole thing f, then its derivative is f prime. Is going to equal the integrand at the upper limit multiplied by the derivative of the upper limit. Essentially, we're working with chain rule. So this is a chain rule problem. Okay. All right. Uh-oh, I got a problem here. The rule for finding the derivative of an integral says that that lower limit of integration needs to be a number. This one isn't. So I cannot do this as it currently sits. So I'm going to have to know this property. Do you remember this property? Where we took a single integral and broke it up into two integrals. Okay. How's that sound? Does that look good? Well, I'm happy with this one. I can do that one, but I'm terribly unhappy with this one, because this needs to be the lower limit and this needs to be the upper limit. So how do I switch my limits of integration? Well, there's a property. Do you remember this property? That the limit from a to b is equal to the negative integral from b to a. So we can just flip the limits of integration by tossing in an extra negative sign. So now I'm going to rewrite the orange again, and now I have f of x is equal to the negative integral from 0 to negative x of t cubed dt plus the integral from 0 to x of t cubed dt. How do we feel about everything? Well, that one's been good. Is this one good now? Well, no, not really. Still has a problem. That's negative x, not just plain old x. And since that is a negative x, then what we're going to have to do is we're going to have to do this one, or that integral as a chain rule. Okay, man. So, now that I know what to do, I can actually start taking the derivative. So there's a negative. That negative is, those are the same one right there. Okay? And then, let's see. When I do a derivative of an integral, I take the integrand, put in the upper limit of integration, and multiply by the derivative of the upper limit of integration, which in this case is a negative 1. Plus, let's see. When I do the derivative of an integral, I take the integrand, plug in the upper limit of integration. Let's see what's going on here. Let's see, negative x cubed is negative x cubed. Makes it a positive. Looks like we got a negative x cubed coming out of this. Plus a positive x cubed. A negative x cubed plus a positive x cubed is 0. So that means that the derivative is 0. That means as x gets bigger, the integral doesn't change size. That doesn't make any sense. Well, let's think about it geometrically. Remember what we learned about integration. The area above is positive. The area below is negative. If x gets a little bit bigger, we add on this little piece over here that's positive. But what do we also add on? This little piece over here that is negative. And will the positive piece be the same size as the negative piece? The same length, just opposite direction. So one's positive, one's negative. They're going to cancel each other out. Okay. I'm going to skip number 6 to come down here, take a look at number 7. And then that's the end of this section. Okay. So let g of x be the integral from 0 to x of f of t dt, where f is the function whose graph is shown at the right. Estimate g of 0, g of 2, g of 4, g of 6, and g of 8. Find the largest open interval upon which g is increasing. Find the largest interval where g is decreasing. Identify any extrema of g, maximums, and make a rough sketch of g. Okay, well, we can do this. So what does g of 0 mean? Well, just going back to the definition, that's the integral from 0 to 0 of f of t dt. Since the lower limit and the upper limit are the same, the value of that integral is 0. So g of 0 is 0. Okay, I can make that make sense. All right. So then what's g of 2? Well, g of 2 is equal to the integral from 0 to 2 of f of t dt. Now, since I don't have any algebra for g, I'm going to have to use the graph over here. And the graph says, do this. Find the area bounded by the curve, the x-axis, and the function f. So I had to figure out what's the area of that piece that I just outlined there. What's the area of this piece? Well, 1, 2, 3, 4, 5, 6, I don't know, can we call that one full one if we put those two together? Mostly, maybe like 6.7-ish. Doing the integral from 0 to 2 of f. Now they want us to calculate g of 4. So that means the integral from 0 to 4 of f of t dt. So let me get rid of this purple because that was from the last problem. They want us to do 0 to 4. So they want us to find all of this. And so what is that approximately? Well, 1, 2, 3, 4, 5, 6, 7 full. 8 if I count those two. 8.7? Okay. Now I'm going to try g of 6. What does g of 6 mean to do? The integral from 0 to 6 of f of t dt. Well, 6 means take it out to here. So now you've got this negative piece. So if this one over here, if we said the positive was about 8.7 positive, how much is that negative? Oh man, I'm going to call that 1. I'm going to call that down there a negative 1. So 7.7. And then what's the last thing they want us to do? G of 8. G of 8 says keep going all the way out to 8. So again, I know the positive piece up above is about 8.7. How much is all that? 1, 2, 3, 3.7. So negative 3.7. And what's 8.7 minus 3.7? About 5. Okay. So all of that was part A of the problem. Very straightforward once I knew what to do. I said, here's a function, go make it happen. All right, part B. The interval for increasing. So for what values of t does the function g get bigger? Well, we went from 0 to 2, it got bigger. Went from 0 to 4, it got bigger. From 0 to 6, though, it got smaller. So when did it stop getting bigger and start getting smaller? Well, the switch occurred right here. Because up till that point, up till 4 on that t-axis, as t grew, more area, more area, more area, we just kept adding more area under it. And since we keep adding more area, g is getting bigger, so it looks like the interval of increasing is 0 to 4. Where is it decreasing? Well, it's decreasing when we start accumulating negative area. And negative area started at 4 and stopped at 8. Does G have any extrema? Is there a highest point? Well, take a look at part B. What did we just get done saying up here in part B? We said that was an interval of increasing, that was an interval of decreasing. And so if I go up and then I go down, what's that called? Ideally, it's called a maximum. And if that's a maximum, then when does that occur? What is the t-value that gives that maximum? And it looks like that t-value was 4. So it looks like we have a maximum at t equals 4. Last part's the hardest. I'm supposed to sketch a rough graph of the function g. Let's see. It goes from 0 and then at 2 it's up at 6.7, and then at 4 it's up at 8.7, and then at 6 it's down to 7.7, then at 8 it's down to 5. Something like that. Or they got kind of ugly there at the end. Something like that. Actually, I can't put an arrowhead on the end of it. I just know it stops there. It stops there. Very rough sketch. Okay. Now this brings us to the end of Chapter 5, Section 3. You should be able to finish the homework up through 5.3. And, well, I guess I can get the exam ready for Unit 7 then. All right, best of luck on it.